Canada's sleeping volcano is awakening, and scientists are terrified by what they found because Mount Baker, just 25 kilometers from the Canadian border, is showing the exact same warning signs that appeared before Mount St. Helens exploded and devastated everything within 200 miles. Picture a massive ice-covered peak towering over Vancouver and the Fraser Valley, home to 3 million Canadians who have no idea they are living in the shadow of the closest active volcano to any major population center in Canada. This is not some distant threat. This is a geological monster that could bury entire cities under lahars, pyroclastic flows, and volcanic debris within hours. But here is what has volcanologists in complete panic. Mount Baker contains more glacial ice than all other Cascade volcanoes, except Mount Rainier combined. When this sleeping giant erupts, all that ice will melt instantly, creating massive lahars that will race down river valleys straight toward Canadian communities at 40 miles per hour. The most terrifying discovery came from recent seismic monitoring, showing unusual deep tremors and ground deformation patterns that match pre-eruption signatures from other Cascade volcanoes. The mountain is literally inflating as magma moves closer to the surface. Is Mount Baker's awakening just normal volcanic restlessness? Or are we watching the countdown to Canada's first major volcanic disaster that could devastate the most populated region of British Columbia? Canada's sleeping volcano is awakening, and scientists are terrified by what they found because Mount Baker, just 25 kilometers from the Canadian border, is showing the exact same warning signs that appeared before Mount St. Helens exploded and devastated everything within 200 miles. Western Canada is not as quiet as it looks. Hidden beneath forests, glaciers, and remote peaks, a chain of volcanic belts stretches from the Yukon border all the way to Vancouver Island. These are not isolated mountains. They are the scars and pressure points of a restless planet. 5 major volcanic belts cut across British Columbia and the Yukon, each shaped by powerful forces deep beneath the Earth. The Garibaldi Volcanic Belt forms the spine of southwestern British Columbia, running north from Vancouver through Whistler to Mount Meagher. Here, snow-capped peaks like Mount Garibaldi and Mount Price rise above alpine lakes and forests, their origins tied to the slow grind of tectonic plates. This belt is the northern extension of the famous Cascade Range, which includes Mount Baker just across the border. To the northeast, the Wells Gray and Clearwater Volcanic Field tells a different story. This region, stretching along the Clearwater and North Thompson rivers, is marked by lava plateaus and cinder cones rather than towering stratovolcanoes. Wells Gray Park is famous for waterfalls, but beneath the surface, it holds evidence of eruptions in the past 10,000 years. These flows once dammed rivers and reshaped entire valleys, creating landscapes that seem peaceful now, but bear the marks of violent change. Further north, the Stikine Volcanic Belt cuts through the rugged Cassiar Mountains and the remote wilderness of northwestern British Columbia. This belt is home to some of Canada's youngest and most active volcanoes, including the hauntingly barren Mount Edziza and the Tsiaks Cone. The eruption of Tsiaks in the 18th century produced lava flows that buried Nisga'a villages and left behind the stark black fields of the Nisga'a Memorial Lava Bed, a living reminder that these volcanoes are not ancient history. The Anaheim Volcanic Belt, stretching across the Chilcotin Plateau, is a line of shield volcanoes and domes formed by a stationary hotspot deep beneath the crust. Over millions of years, the North American plate has drifted over this plume, leaving a trail of volcanic peaks like Nazca Cone and the massive shield of Rainbow Range. The Anaheim Belt's eruptions are less explosive, but they have covered vast areas with thick basalt flows, shaping the heart of British Columbia's interior. In the far northwest, the Wrangell Volcanic Belt crosses into Yukon and Alaska. This is a land of glaciers and remote summits, where volcanoes like Mount Churchill have sent ash clouds as far as Greenland. The White River ash, blown across the Arctic 1,200 years ago, is a silent witness to the power these volcanoes can unleash. Each of these belts tells a story of fire, ice, and slow-motion catastrophe. Together, they form a hidden lattice of risk beneath Canada's most beautiful landscapes. For most Canadians, these volcanoes are distant, almost mythical. But their eruptions have shaped rivers, buried forests, and in some cases wiped out entire communities. And while most remain silent today, the ground beneath British Columbia and Yukon is anything but still. Canada's sleeping volcano is awakening, and scientists are terrified by what they found, because Mount Baker, just 25 kilometers from the Canadian border, is showing the exact same warning signs that appeared before Mount St. Helens exploded and devastated everything within 200 miles. Eruptions in Canada are not just stories buried in the deep past. They have left scars and memories that still shape entire regions. In the heart of British Columbia, Mount Meager stands as a warning written in ash and stone. About 2,350 years ago, Meager unleashed the largest known volcanic eruption in Canada's recent geologic history. The blast sent a plume of ash high into the atmosphere, blanketing valleys for hundreds of kilometers. Rivers were blocked, forests flattened, and the land was transformed overnight. The evidence lies in thick layers of volcanic debris, still visible today along the Lillooet River Valley. For the people who lived nearby, there would have been no escape from the choking ash and the rivers of mud that followed. Scientists estimate the eruption rivaled some of the most notorious blasts in North America, yet few outside the region know the name Meager. But the most haunting chapter belongs to the Nisga'a people of the Nass River Valley, far to the north. In the late 1600s or early 1700s, the Seax Cone erupted with deadly force. Lava surged down the Seax River, burying entire villages and blocking the Nass. Yet it was not the lava alone that killed. Nisga'a oral histories describe how invisible clouds of volcanic gas, likely carbon dioxide, pooled in the valley bottoms as people slept. Hundreds, possibly up to 2,000, died in their homes and camps, suffocated in the darkness. The land itself became a memorial. Today, the Nisga'a Memorial Lava Bed preserves both the hardened flows and the memory of those lost beneath them. It stands as a sacred warning that even a modest-looking volcano can deliver one of the deadliest natural disasters in Canadian history. Farther west, hidden deep in the Coast Mountains, the Silver Throne caldera dwarfs even these stories in scale. This remote, ice-filled basin stretches over 31 kilometers across, evidence of a super eruption that may have been the largest in the entire Cascade Arc. The eruption that formed Silver Throne happened long before written memory, but the caldera's size hints at an event powerful enough to darken skies across continents. Today, Silver Throne's silence is deceptive. Its vast, glaciated expanse is a reminder that some of Canada's greatest volcanic threats lie in places few people ever see, waiting for the right combination of forces to awaken them again. These eruptions, Meager's ash, Seax's deadly gases, and Silver Throne's hidden scars, are not distant myths. They are proof that Canada's volcanoes can destroy landscapes and end thousands of lives in a matter of hours. Maps and hazard models become real when you walk the lava beds or stand in a valley once buried by mud and fire. The stakes are not theoretical. They are written into the land and remembered by those who survived, or whose ancestors did not. In a country where most people have never felt a tremor or seen a plume of ash, the evidence is clear. The sleeping giants have awakened before, and they can do so again. March 1975, a plume of steam and gas burst from Sherman Crater on Mount Baker, startling scientists across the Pacific Northwest. New fumaroles, hundreds of them, punched through the snowpack, doubling the size of the crater's bare, steaming ground in just days. Pools of acidic, sulfurous water collected in freshly melted pits, some hot enough to scald. The air reeked of rotten eggs, and runoff in Boulder Creek turned milky and sour, with a pH barely above battery acid. Within weeks, university researchers and federal geologists converged on the mountain. They scrambled to install seismic sensors and thermal probes, racing to answer a question no one wanted to ask. Was Baker about to erupt? The memory of Mount St. Helens' quiet slopes still loomed large, and no one wanted to miss the next warning sign. Helicopters ferried equipment to the crater rim, while teams fanned out to sample water and gases. Every reading was scrutinized for signs of magma on the move. Downstream, the threat felt immediate. Baker Lake, held back by the Upper Baker Dam, became a focus of urgent action. Engineers worried that a sudden landslide or an avalanche triggered by an eruption could send a wall of water surging over the dam. In a move that made headlines, authorities ordered that the lake's water level be lowered by more than 10 meters. Access to the lake and dam was cut off. The mood was tense. One wrong move from the volcano, and the entire valley could be at risk. For months, the mountain steamed and hissed. But the instruments told a quieter story. Seismic activity remained low, with no clusters of earthquakes or deep tremors that would signal magma rising. Geophysical surveys found no evidence of inflation or new magma intruding beneath the crater. By late summer, the sense of crisis faded. The steam surge was traced to shifting heat flow in the hydrothermal system, not an impending eruption. Still, the scars of 1975 lingered in memory, a reminder that Baker can go from silence to alarm in a matter of days, and that the next warning may come just as suddenly. Mount Baker's white crown isn't just for show. Beneath the summit, nearly 2 cubic kilometers of glacier ice and perennial snow cling to the slopes, more than any Cascade volcano except Mount Rainier. That frozen mass, spread over 38 square kilometers, is a silent reservoir of disaster. In a major eruption, or even a sudden collapse of the crater's hydrothermally weakened walls, volcanic heat and debris could melt millions of tons of ice in minutes. The result? Lahars, raging torrents of mud, rock, and water, barreling down the mountain's flanks. Lahar models for the Cascades are blunt. When hot pyroclastic flows or avalanches sweep across glaciers, they can unleash concrete-thick rivers, racing at highway speeds. In the steep upper valleys, surges can reach up to 40 miles per hour, fast enough to outrun a car, obliterating everything in their path. These flows don't politely stop at the US border. They follow gravity, scouring riverbeds and swallowing forests, bridges, and farms. Within an hour, a lahar could travel from Baker's summit into the lowlands, carrying boulders and logs the size of trucks. A glaciologist who has spent decades tracking Baker's retreating ice described the danger plainly. It's not just the eruption you worry about, it's the instant, massive melt. That's what turns a volcano into a flood machine. Even a moderate event can send a wall of debris roaring down the Nooksack or Baker River, threatening communities miles downstream. The physics are simple and merciless. More ice means more water, more momentum, more destruction. Baker's vast ice cap is a loaded gun, primed by heat and gravity, waiting for the trigger. A quiet mountain can hide a restless heart. In recent years, a new kind of anxiety has crept into the labs and offices of the Pacific Northwest's top volcanologists. Their attention is fixed on the subtle signals coming out of Mount Baker, signals that would barely make a ripple in the news, but which, to those who know what to look for, are anything but routine. Seismic monitors have picked up clusters of deep, low-frequency earthquakes, small muffled thuds far below the surface. These are not the sharp cracks of rock breaking under tectonic stress. Instead, they pulse at 1 to 3 hertz, a spectral fingerprint of fluids or gases shifting deep underground. At Baker, these low-frequency events are more common than at most other Cascade volcanoes. While some scientists believe they are tied to water and gas moving through hot rock, others worry they could be the faint heartbeat of magma on the move. But it is not just the tremors. Sensitive instruments have tracked tiny changes in the shape of the mountain itself. Subtle ground swelling measured in millimeters that could indicate magma is pressing upward, inflating the volcano like a slow-motion balloon. These patterns echo the earliest warning signs seen at Mount St. Helens in the months before its catastrophic 1980 eruption. There, it started with deep tremors and slight deformation, barely perceptible at first, but building steadily until the mountain tore itself apart. The difference is scale and exposure. Mount Baker sits just 25 kilometers from the Canadian border, with over 3 million people living in its shadow. Most have no idea that the same kinds of signals that once preceded a historic disaster are now being quietly logged and debated by experts. As one USGS volcanologist put it, we would rather be accused of overreacting than of missing the one signal that matters. The stakes are not academic. If these signals are the first stirrings of unrest, the clock could already be ticking. And with every new tremor, every millimeter of uplift, the need for better, faster monitoring becomes more urgent. Mount Baker is watched by some of the best volcano scientists in North America, but even the experts admit they are working with a blurry picture. The current seismic network on and around the mountain is shockingly thin, and just 2 local seismometers feed into the Pacific Northwest Seismic Network. For decades, the only station close to Baker was UW.MBW, an analog unit installed in the early 1970s and located about 40 kilometers from the summit. That single vertical component sensor was the sole set of ears on Baker's deep rumbles for nearly 30 years. Only in the 2000s did a second local station come online, but the network remains sparse compared to what is in place at Mount St. Helens or Mount Rainier. This matters because with so few instruments, only earthquakes larger than about magnitude 1.2 can be reliably detected and located. Anything smaller, a subtle pulse of magma, a faint, deep tremor, or a low-frequency quake, could slip by unnoticed. The reality is that the earliest signs of a volcano waking up are often the quietest. Without a dense web of sensors, early warning is a matter of luck as much as science. Most volcano monitoring experts recommend at least 6 to 10 broadband seismometers spaced around the edifice to catch the full spectrum of volcanic unrest. Baker has a fraction of that. The gaps are not just academic. They mean that the region's 3 million residents are depending on a system that could miss the first crucial hours of a crisis. For communities in the Fraser Valley and beyond, the difference between a near miss and a disaster might hinge on whether a tiny tremor is heard or lost in the static. An early morning in the Fraser Valley starts like any other. Dairy trucks rumble down gravel roads, and fields stretch out beneath the shadow of Mount Baker. But for those who know the land's history, the calm is uneasy. In a farmhouse kitchen, a Stolo elder recalls stories passed through generations. Memories of sudden, unstoppable floods that swept away entire fishing camps. These are not just legends. They are warnings, rooted in lived experience, of how water and earth can turn against those who ignore the signs. Across the valley, a dairy farmer stands by his barn, calculating what it would take to move hundreds of cattle if the rivers rise. There is no official plan for an eruption. Evacuation routes are mapped for fires and floods, not walls of mud and debris racing down from the south. The farmer shakes his head. Moving people is one thing, but moving livestock is another. Hours count, and so does every decision. In a windowless municipal office, emergency managers gather around a table scattered with maps and hazard models. They run a tabletop exercise, tracing the path of a hypothetical lahar from Baker's slopes into the Nooksack River, across the border, and toward the heart of the Fraser Valley. The scenario is clear. Within an hour, entire neighborhoods could be cut off, bridges lost, farmland buried. Yet as the exercise ends, the reality sets in. There is no dedicated binational plan for a Baker eruption, no cross-border drills. Funding is tight, and volcanic risk rarely makes the budget. The meeting ends with a question hanging in the air. Wait for more data, or act now to prepare for the disaster that history says will come? For the people living in Baker's shadow, the decision is anything but theoretical. Mount Baker sits silent, yet its potential looms over millions. Today, more than 3 million Canadians live within reach of its icy shadow, largely unaware of the risk beneath their feet. As cities grow and climate shifts accelerate glacier melt, the margin for error narrows. Preparedness isn't panic, it's survival. The true danger is never the mountain. It is ignoring the warning signs. What would you do if the siren sounded tomorrow? Yesterday, California's coastline sat at sea level. Today, it is towering 6 feet above the waves, leaving harbors stranded and marine life exposed on dry land. Scientists built their careers on the idea of gradual change, but this was instant, stretching for hundreds of miles. It is not just the speed that terrifies experts. A city block-sized, eerily geometric void has appeared beneath the coast, filled with a material unlike anything known on Earth. Could this be the warning sign of a disaster no one saw coming? Marin Govorchin has spent decades tracking every subtle motion along California's rugged edge. For most of that time, the coastline barely seemed to move at all. Tectonic plates grind past each other beneath the state, but their effects are measured in fractions of an inch each year, sometimes as little as 0, sometimes up to 4 millimeters. That's less than the width of a pencil tip, spread out over 12 months. In places like the Santa Barbara Basin or Long Beach, scientists have documented the land rising by a few millimeters per year, often tied to groundwater recharge or oil field operations. Even these so-called uplift hotspots are modest, and they unfold so slowly that only the most sensitive equipment can spot them. Govorcin's team at NASA's Jet Propulsion Laboratory relies on satellite radar and a dense web of GPS stations to watch for these changes. Each instrument is tuned to detect the smallest vertical shifts, down to the millimeter. Over the years, the data has painted a picture of a coastline in perpetual, gentle motion. Sometimes, the ground sinks as water is pumped from deep below. Other times, careful management of aquifers or oil fields nudges the land upward. But the pace is always glacial, never sudden. The largest changes on record, like the slow bulging at Portuguese Bend or the gradual rebound in Long Beach, accumulate over years, not hours. This slow dance between land and sea has shaped every scientific model and every coastal policy. The idea that California's shore could leap upward by feet in a single night runs counter to everything Marin Govorchin and his colleagues have ever measured. Their instruments are built for patience, not panic. For decades, the numbers have told a story of change at the edge of perception, steady, predictable, and, above all, slow. That's why, when the alarms finally sounded, no one was prepared for what came next. Dr. Eric Fielding arrived at the Jet Propulsion Lab before dawn, laptop in hand, determined to rule out the most basic explanation, a technical glitch. Every GPS station from Crescent City to San Diego had registered the same impossible leap, upward by as much as 6 feet, within a single night. Fielding's team started with the raw logs. They pulled minute-by-minute records from over 400 coastal GPS units, hunting for signs of interference, power failure, or sudden shifts in satellite geometry. Each station's data was compared against its nearest neighbors. No outliers, no drifting clocks, no evidence of spoofing or cyber attack. Next came the satellite radar. Sentinel-1 interferograms, processed through Jet Propulsion Lab's automated pipeline, showed the coastline's elevation change as a sharp, unbroken step. Pixel after pixel, the same pattern repeated across hundreds of miles. Atmospheric corrections were checked and recalibrated. The results did not budge. Tide gauge records, downloaded from NOAA's observation network, told the same story from another angle. Water levels at every major harbor had dropped by nearly 2 meters in a matter of hours, far beyond the normal swing of tide or storm surge. Barometric pressure, wind, and storm data all failed to account for the change. Fielding's team ran through every known error source: multipath interference, data reference frame shifts, sensor drift, even the possibility of a coordinated equipment malfunction. Each possibility was tested and eliminated.